All right, let's dive into the fascinating world of lightning and thunder by first understanding the process of charge separation within a storm cloud. And this is the very foundation of how lightning forms, so it's important to have a good grasp of this concept. Now imagine a storm cloud forming in the sky. Now, as it grows, there's a lot of activity happening inside it. Tiny ice particles and water droplets are constantly colliding with each other, and this movement causes the particles to become electrically charged. Over time, the charges within the cloud start to separate, with the positive charges gathering at the top and the negative charges at the bottom. This charge separation creates an electric field within the cloud, and as it continues to grow, the electric field becomes stronger. Eventually, the electric field becomes so strong that it starts to break apart the air molecules in the atmosphere, turning them into charged particles called ions. Once this ionization process occurs, we can say that the stage is set for lightning to form. The air has now become a conductor, making it easier for the electrical charges within the cloud to move around and potentially connect with other charges, either within the cloud itself or on the ground. And there you have it. This is the basic process of charge separation that occurs within a storm cloud, ultimately leading to the formation of lightning. But this is just the beginning of the story, as the movement of air within the storm plays a significant role in the development and intensity of lightning and thunder. So let's move on to our next topic, the role of updrafts and downdrafts in a storm. Now that we've understood the process of charge separation in a storm cloud, let's delve deeper and investigate the role of updrafts and downdrafts during a storm. These two phenomena significantly influence the movement of ice particles and water droplets, which in turn contributes to the charge separation process that leads to lightning. Updrafts are essentially upward-moving air currents within a storm cloud. They occur when warm, moist air near the Earth's surface rises due to its lower density compared to the colder air above. As this warm air rises, it cools and condenses, forming the towering cumulonimbus clouds we typically associate with thunderstorms. Now, these updrafts play a vital role in moving the ice particles and water droplets within the cloud. As the particles and droplets are carried upwards, they collide with one another, and through this process, they become electrically charged. Remember, this is the foundation of the charge separation process we discussed earlier. On the other hand, downdrafts are downward-moving air currents caused by the sinking of cooler, denser air within the storm cloud. These downdrafts also contribute to the movement of ice particles and water droplets, as they force the charged particles downwards towards the base of the cloud. In essence, the combination of updrafts and downdrafts creates a continuous cycle of particle movement within the storm cloud. This constant churning and colliding of particles enhances the charge separation process, ultimately increasing the likelihood of lightning formation. So there you have it. Updrafts and downdrafts play a crucial role in facilitating the movement of ice particles and water droplets within a storm cloud, directly contributing to the charge separation process that leads to lightning. With this knowledge in hand, let's move on to our next topic and learn about the different types of lightning and the mechanisms that cause them to occur. Now that we have a solid understanding of the charge separation process and the role of updrafts and downdrafts in storms, let's dive into the different types of lightning that can occur. Mainly, we'll focus on three types: cloud to ground, cloud to cloud, and intracloud lightning. Each type has its unique characteristics and mechanisms that cause them to occur. First, let's talk about cloud to ground lightning, which is probably the most familiar type for many of us. As the name suggests, this type of lightning occurs when an electrical discharge connects the negatively charged base of a storm cloud to the positively charged ground below. This connection creates a path for the electrical current to travel, resulting in a brilliant flash of lightning. Cloud-to-ground lightning can be exceptionally powerful and is responsible for most of the lightning-related injuries and fatalities that occur each year. It's also the type of lightning that can cause fires and damage to infrastructure, such as power lines and buildings. Next, let's discuss cloud-to-cloud lightning. This type of lightning occurs when an electrical discharge connects two separate storm clouds, or different regions within the same cloud. In this case, the lightning travels between the positively charged upper regions of one cloud and the negatively charged lower regions of another cloud, or the same cloud. Cloud-to-cloud lightning is typically less dangerous than cloud-to-ground lightning, since it doesn't directly involve the ground. However, it can still be a spectacular sight to behold, as the lightning flashes illuminate the sky. Finally, let's explore intracloud lightning, which is also known as sheet lightning, or anvil crawler lightning. This type of lightning occurs entirely within a single storm cloud, as electrical discharges travel between the different charged regions of the cloud. Intracloud lightning is the most common type of lightning, but is often hidden from view due to the dense cloud formations. The mechanisms that cause these different types of lightning to occur are all based on the same fundamental principles of charge separation and electrical discharge. It's mainly the specific configuration of charged regions and the path of least resistance that determines the type of lightning that will take place. So now that we've learned about the various types of lightning and the mechanisms behind them, let's move on to our next topic, which is the relationship between lightning and thunder. Now that we have a good understanding of the different types of lightning, it's time to examine the relationship between lightning and thunder. You might have noticed that every time you see a lightning flash, you also hear the accompanying sound of thunder. But have you ever wondered why this happens? Let's explore the science behind this fascinating phenomenon. When a lightning strike occurs, it generates a tremendous amount of heat. We're talking about temperatures that can reach up to 30,000 Kelvin, or around 5 times hotter than the surface of the sun. This intense heat causes the air around the lightning channel to expand rapidly, creating a shock wave that moves through the atmosphere. This shock wave is what we perceive as the sound of thunder. As the shock wave travels through the air, it compresses the air molecules, creating a series of pressure waves that our ears detect as sound. The rumbling noise that we often associate with thunder is actually the result of these pressure waves echoing and reverberating through the atmosphere. It's also worth noting that the speed of light is much faster than the speed of sound, which is why we see the lightning flash before we hear the thunder. If you're curious about how far away a lightning strike is, you can use the flash to bang method. Count the number of seconds between seeing the lightning and hearing the thunder, then divide that number by 5. The result will give you a rough estimate of the distance in miles. In summary, the relationship between lightning and thunder is quite simple. The rapid heating and expansion of air due to a lightning strike produces a shock wave that manifests as the sound of thunder. This process is a fascinating example of the incredible power of nature and the complex interactions between the different elements of our atmosphere. With this knowledge in hand, let's move on to our final topic and explore the factors that influence the frequency and severity of lightning and thunderstorms. As we wrap up our discussion on lightning and thunder, let's explore the factors that influence the frequency and severity of these awe-inspiring events. The occurrence and intensity of lightning and thunderstorms are influenced by various elements, including climate, geography, and weather patterns. By understanding these factors, we can better predict and prepare for these natural phenomena. First, let's consider climate. The overall climate of a region plays a significant role in determining the likelihood of lightning and thunderstorms. Regions with warm, humid climates, such as tropical and subtropical areas, are more prone to thunderstorms due to the availability of moisture and heat. These conditions fuel the development of powerful updrafts, leading to the formation of large cumulonimbus clouds and eventually resulting in lightning and thunder. Next up is geography. The physical features of a region, such as mountains, valleys, and large bodies of water, can significantly impact the occurrence of thunderstorms. For example, mountain ranges can force warm, moist air to rise, creating the perfect conditions for storm development. In contrast, large bodies of water, like oceans and lakes, can help moderate temperatures and increase humidity, also contributing to the formation of storms. Finally, Weather patterns play a crucial role in the frequency and severity of lightning and thunderstorms. Certain weather phenomena, like cold fronts, can trigger the development of storms by forcing warm air to rise quickly, leading to the formation of cumulonimbus clouds. Additionally, large-scale weather systems, such as the El Niño Southern Oscillation, can influence storm patterns by altering global wind and temperature currents. In conclusion, the factors that influence the frequency and severity of lightning and thunderstorms are complex and interconnected, with climate, geography, and weather patterns all playing a role. By understanding these factors, we can better appreciate the intricate dynamics of our atmosphere and the awe-inspiring power of nature's light show. So the next time you witness a brilliant flash of lightning or hear the rumble of thunder, take a moment to appreciate the incredible atmospheric conditions and processes that have come together to create such a captivating spectacle.